In this video series, we're going to look at the branch of electrochemistry dealing with galvanic cells. We'll look at how we can predict what will happen when a metal is submerged in a solution of a different metal, and how to measure or harvest the energy like we do in batteries. We'll also look at how to calculate the standard potential of a galvanic cell, and in the second video, I'll show you how you can use the Nernst equation to calculate the potential if the reaction conditions differ from the standard conditions. To understand what happens in a galvanic cell, we must first refresh our knowledge of redox chemistry. When something gains electrons, we say that it has been reduced, and when something loses electrons, we say that it has been oxidized. A great way to memorize this is the word oil rig, which can be an acronym for oxidation is loss, reduction is gain. There must always be balance, meaning preservation of charge. Electrons can't just disappear into the blue, so if one element is being reduced, it must mean that another element is correspondingly oxidized. We must have both an electron donor and an acceptor. The oxidation number tells us whether a substance is missing electrons or has a surplus. For simple metal ions, like we're looking at in this video, the oxidation number is simply equal to the charge. This means that iron 3 ions, like we have here, have an oxidation number of +3. We write that in Roman numerals, and copper 2 ions have an oxidation number of +2, whereas solid copper or any solid metal has the oxidation number 0 because it doesn't have a charge. Oxidation is an increase in oxidation number, i.e. a loss of electrons, while a reduction is a decrease in oxidation number, i.e. a gain of electrons. It's a good idea to have a memory trick for this because we now introduce the terms reductant and oxidant. A reductant is something that reduces something else, meaning that it donates electrons and must therefore undergo oxidation itself. Likewise, an oxidant is something that oxidizes something else, meaning that it steals the electrons and thus undergoes reduction itself. We are now ready to look at what happens when we submerge a metal in a solution. Let's begin by looking at plain water with a magnesium rod. Some of the atoms from the magnesium rod will go into solution and become magnesium 2 ions. The electrons will remain in the rod, thus giving it a negative charge. Because of charge attraction, the positive ions will remain close to the rod, and some of them will regain the electrons and rejoin the surface as a solid metal. This is an equilibrium that is reached over time, meaning that at some point the number of atoms leaving the rod as ions will be equal to the number of ions rejoining the surface. The net result is that the rod will be negatively charged while the surrounding solution will be positive. In general terms, we can write this reaction as M, which just stands for any kind of metal on solid form, is in equilibrium with its metal ions, which we just write as N+, because it could be 2+ like magnesium or 3+ like iron, for example, plus N number of electrons. Some metals are more willing to react than others. If we were to perform the same experiment with copper rather than magnesium, we wouldn't achieve as negative a charge because the equilibrium for copper is shifted further towards the right, towards the solid state, than it is for magnesium. This difference in reactivity is crucial as to what happens when we mix two different metals. Let's take a look at how zinc and copper behave towards each other. We have two scenarios. In the first, we lower a copper rod into a solution containing zinc ions. In the second scenario, it's the other way around. A zinc rod is lowered into a copper solution, which, as you may know, is blue. What do you think will happen? It turns out that nothing happens in the first scenario, but in the second beaker, the copper ions will take electrons from the zinc rod and coat the surface in a layer of copper. This removes some of the blue color because this was caused by the copper ions. Meanwhile, some of the solid zinc will go into solution as ions. The reaction can be written as solid zinc plus copper ions is in equilibrium with zinc ions and solid copper. Copper is being reduced, meaning that it's acting as an oxidant, while zinc is being oxidized, meaning that it's acting as a reductant. Zinc is a stronger reductant than copper, and this is why we don't see a reaction in the first scenario. Here, the equilibrium looks like this. We have solid copper plus zinc ions becomes copper ions plus solid zinc. Copper is a lot better at holding on to its electrons than zinc is, so the equilibrium is shifted far towards the left, whereas in the other scenario it was shifted more to the right. Notice how in both cases the equilibrium is shifted towards the side with the solid copper. It's important to know that it's all relative. The reaction happens because copper is relatively better at holding on to its electrons compared to zinc. Had we instead done the experiment with gold and copper, it would be gold that held on the tightest to its electrons. We exploit this fact when gold plating jewelry, where gold ions can be made to coat the surface of, for example, copper or silver in the same way copper coats a zinc surface. In this way, we can rank all the elements in what is known as the electrochemical series, of which you can see a sample here. The elements at the bottom do the best job at keeping their electrons, and they won't easily undergo chemical reactions. This is why we refer to them as precious metals. The elements at the top, however, are very willing to part with their electrons and are therefore very reactive. You may have seen how a piece of sodium or potassium reacts when dropped into water, very explosively. Conversely, not a lot happens when you drop a piece of gold into water. In redox terms, we say that the elements at the bottom are the best oxidants, while the ones at the top are the best reductants. Because everything is relative, hydrogen has been agreed upon to be a reference point or 0 point. But what are we actually measuring? The number that decides where in the electrochemical series an element is placed is called the standard potential, which we denote as E0 or E0. It's a measure of the potential difference that arises between the given substance and the hydrogen reference. If we go back to our experiment with copper and zinc, we can't just measure the potential difference by sticking an electrode into the solution, because the exchange of electrons is only happening locally around the zinc rod. This also means that we can't harvest the energy. So we need to separate the oxidation process from the reduction process physically. This allows us to install a voltmeter between the two reactions and measure the potential difference. A setup like this is called a galvanic cell and consists of two so-called half cells. Each half cell consists of a metal rod, also called an electrode, submerged in a solution of the same metal. Over here we could have a zinc rod submerged in a solution containing zinc sulfate, and over here we could have a copper electrode submerged in a solution containing copper sulfate. The sulfate ions do not participate in any reactions, they're merely spectator ions, so we will be ignoring them from now on. The two electrodes are connected by a wire, along which a voltmeter can be installed. When zinc goes into solution, becoming zinc 2 ions, the resulting electrons will travel along the wire and go into the copper electrode, where copper ions can accept them and become solid, thus coating the surface of the copper electrode, like we saw before. This allows us to not only measure the potential difference, but also to harvest it, which is the basic principle in galvanic batteries. The last component of the galvanic cell is the so-called salt bridge. This prevents charge from building up in the individual half cells. Without the salt bridge, the right cell would accumulate a negative charge since electrons are continually being supplied from the other electrode. This would effectively stop the reaction because if the right cell becomes negative, no more electrons would go there. To avoid this, we install a salt bridge between the cells. The salt bridge contains counter ions that can diffuse into the half cells and neutralize the charge. For example, our salt bridge could consist of potassium chloride, where the chloride ions would diffuse into the left cell to neutralize the surplus of zinc ions being generated. The potassium ion can likewise travel into the right cell to counteract the lack of copper ions that arises whenever copper ions are removed from the solution to become solid. All elements have been measured against the hydrogen reference in a setup like the one we just saw under standard reaction conditions, defined as 25 degrees Celsius, a pressure of 1 atmosphere, more precisely 100,000 Pascal, and 1 molar of each of the dissolved ions in the respective half cells. This gives us the so-called standard potential denoted as E0. There exists a lot of different tables where you can look up the value for the different substances, and one of the most comprehensive ones can be found on Wikipedia. Here you can sort the list according to the size of the standard potential, which gives us basically the electrochemical series, or you can sort it alphabetically to quickly locate a specific element. But pay attention! Iron, for example, has 14 different entries, and some of them are just molecules that contain iron, but even pure iron has 3 different entries. Here we have iron 2 ions going solid, and here we have iron 3 ions going solid, and down here we have iron 3 ions becoming iron 2 ions. It's important to choose the right species, so you have to consult your reaction scheme. For the remainder of this video, we will be looking at a galvanic cell consisting of a chromium electrode submerged in a solution of chromium 3 ions and a nickel electrode submerged in a solution of nickel 2 ions. We can find the standard potentials in the table on Wikipedia or in a textbook, and we see that the standard potential of chromium 3 plus to solid chromium is minus 0.74. And the standard potential of nickel 2 to solid nickel is minus 0.25. Please note that even if we were to reverse the reactions, the sign of the potential does not change. The fact that both numbers are negative means that both chromium and nickel are worse at holding on to their electrons than hydrogen is. Chromium even more so than nickel because its number is the more negative of the two. Generally speaking, a reduction will occur in the half cell with the highest standard potential. In this case, nickel, because minus 0.25 is a higher number than minus 0.74. An oxidation will occur in the cell with the lowest potential. Remember our oil rig rule. Nickel is being reduced, i.e. it gains electrons, and that's because nickel is better than chromium and holding on to its electrons. Now we have the standard potentials of the individual metals measured against the hydrogen reference. But what happens when we combine the two half cells in a galvanic cell? We can calculate a standard potential for the entire cell, denoted E0 cell, by subtracting the standard potential of the left cell from the right cell, that is E0 right minus E0 left. But which cell is right and which is left? By convention, the electron donor should always be on the left so that electrons flow from left to right. In our case, chromium is the reductant or the donor, so we write chromium on the left and nickel on the right. So this becomes E0 nickel minus E0 chromium. And we have the numbers up here. So if we insert them, minus 0.25 minus 0.74. This gives us 0.51 and the unit is volt. This is the standard potential of the galvanic cell containing chromium and nickel. If we were to draw our galvanic cell, it would look like this. A chromium electrode in a chromium solution on the left and a nickel electrode in a nickel solution on the right. The electron donor is also called the anode, and the acceptor is called the cathode. To avoid drawing the whole setup every time, we can instead draw a so-called cell diagram. We start by writing the anode. So we have chromium solid and we have chromium ions. A vertical line represents the barrier between the solid and aqueous phases. The salt bridge between the cells is represented by two vertical lines. And on the other side, we write the cathode like we did the anode. So we have nickel 2 plus ions and a barrier between the phases and solid nickel. Note that we always write the aqueous species towards the salt bridge in the middle and the solid species on the far sides. Let's recap what we've learned so far. Metals are ranked in the electrochemical series according to their reactivity. Hydrogen is the universal reference point against which all other metals are measured. The standard potential, E0, can be found in tables, for example on Wikipedia or in a textbook, and it's defined as the potential under standard conditions, which are 25 degrees Celsius, 1 atmosphere's pressure, and 1 molar of each of the solids in the half cells. A galvanic cell consists of two half cells connected by a wire. The standard potential of the cell can be found by this formula, meaning that we subtract the standard potential of the left cell from the right cell. By convention, the left cell always contains the electron donor, also called the reductant or anode, and it's the cell with the lowest standard potential. On the right side, we have the electron acceptor, also called the oxidant or cathode, and it's the cell with the highest standard potential. Join me in the next video where I will show you how to use the Nernst equation to calculate the cell potential if our reaction conditions differ from the standard.